Calculus!
This is AP Calculus. Lesson 10-2. All right, today's a real lesson. It's a hard lesson. We're talking about the second fundamental theorem of calculus. There are two of them. And there's chain rule on one of them as well.
Can we have like a third of the lights?
A third of the lights? Yeah, sure. That works. Yeah, so today is the 5th of March, 3/5. If you're watching this video in the future, the reason we're so far behind is because we had multiple snow days in a row. So, analyzing derivatives. This should all be reviewed theoretically. Let's see what you guys got. And Arrow, have a whiteboard ready. All right, F increasing. What is the definition of F increasing? There's three symbols. F increasing is where what? F increasing. Well, it's the F prime test, so probably F prime is going to be in here. I'll write one of the three symbols for you. Whew.
F prime is greater than 0.
Greater than 0. F decreasing, Arrow. There it is, F prime less than 0. I can read upside down. And Rochelle, F, CV, the critical values are where F prime or DNE. Yeah, you got both of them. DNE. Write it down. You need to have these memorized. All right. F relative extrema. Where did that happen? We're still in F prime test. F prime test occurs for both the left two columns. The second derivative test is the right column. F relative extrema, I'll write the F prime for us. F prime, Ben.
F prime equals 0.
Not necessarily. F prime equals 0 is FCV.
Or F prime sign change.
There it is. F prime sign change. Arrow, you're going to get the next one. F prime sign change. Oh, come on. The Mimia board has been giving me issues all today. I'm going to have to probably go sit back down. All right. F min is where, yes, F prime changes from a negative to a positive. And Rochelle, F max is where F prime. Oh my God, why does this happen? For some reason, I think the pen might be dying. I don't know what's going on. F prime goes from a positive to a negative. All right, second derivative test. F is concave up where, Ben?
Where F double prime is greater than 0.
F double prime greater than 0. Arrow. Yes, F double prime less than 0. And Rochelle.
When F double prime equals 0?
Ooh, careful.
When
It's a good guess. It's a common misconception, though. Where F double prime.
isn't equal to 0.
Sign change, right?
Yeah, it's a sign change. It's very similar to a relative extrema. F double prime sign change.
Oh, is that when that gives you a number and then it's depending on the slope?
So it doesn't depend on the slope. I mean, if you're looking at a graph of F prime, then it's slope, but it's just looking at the second derivative if you have a sign change. So if your second derivative is positive and then the second derivative goes to a negative, then that means you have an inflection point happening. An inflection point means you'll probably have one of these other things as well. All right, so that's our review. No questions thus far? All right. So we have three types of integrals. It's time to classify them. And these aren't fancy words that I'm making up or John is making up. If you type in accumulation integral, you will get an actual accumulation integral. So indefinite integral. Let's do the same curve for each of these. So I'm going to just do like a whoop. Oh, okay. I give up. I'm sitting back down. I can't handle the Mimia board being imprecise and not even working the way that I want it to.
Does it need to be calibrated?
I calibrated it again this morning. I don't know what's going on. All right, let's do a little whoop, and a little whoop. Roughly the same graph. All right, indefinite integral. That's where what happens? How much area do I have for an indefinite integral?
Well, you don't know.
You kind of do know.
Isn't it supposed to be
Infinite area. That's because we don't have bounds. So generally speaking, when you have an indefinite integral, usually it's saying if I have this function, what is the indefinite integral? And you just take the antiderivative and you give back a function. But in terms of the area under the curve, it's infinite. Infinitely negative or positive, depending on where your curve is.
You know how else you can find out if it's infinite? Infinity? Indefinite.
Oh, yeah, indefinite, and like it has the finite
What if
finity.
it's like a function that just goes, it's like positive and then it's negative and it's perfectly standard on the x-axis?
Like a sine wave.
Yeah.
Then, yeah, that one doesn't actually converge.
So
Oh, man.
it's 0.
It's not zero.
The area.
It doesn't converge. So it's a really fun idea, like asking if area converges, and it's a BC calculus question. I really wish I could talk about it more, but it's like this giant area that's like, well, these telescoping don't converge, and these minor telescoping do converge. There's some very specific rules on whether or not area and series in general converge, but it's a topic for another day, and it's really fun. But in general, the sine wave area does not converge because it fluctuates so much. If you fluctuate and you never get closer and closer, then you don't converge to anything. So this is going to be the antiderivative, so the integral of, we'll just say we're taking the integral of a rate. So if I'm taking f, then the derivative of f prime of x dx. That's what it looks like symbolically. All right, but the definite integral, what does it look like in terms of the graph? What's different from the indefinite integral?
You have bounds.
We have bounds. We have these little, let's say our bounds are from A to B. Then I do a little, do I have the technology to do this? Can he do it? I don't have a dashed line, but I can still do an orange line. So I'm talking about this area. I have a curve on top, which makes it a little bit hard to find, but we have calculus. Calculus was invented because curves are hard, and we can find the exact area underneath the curve using a definite bound from A to B, definite integral of A to B of some f prime of x dx. And it doesn't necessarily need to be f prime of x. This whole unit, all of unit 10, deals with taking the antiderivative of rates. I mean, that's how we started off 10-1 yesterday. So we're always going backwards from rates. And then finally, accumulation. We saw a hint of this yesterday. This is where, maybe you guys want to take a guess at this. Should I just reveal it? Accumulation. We saw this yesterday. You start somewhere. So let's say we start at A. Sometimes we start at 0, and then it just goes on and on and on. So we'll say A, and then you might want an x1 there, maybe an x2 there. We don't know where we're going to end, but we know where we're going to start. So we know the start, don't know the end. So let me come back here and make a line and say we don't know where we end, but we definitely start at A. Good enough. I know slightly diagonal. And it goes on and on forever this way. So I'm going to do like a little arrow that says it goes on and on forever that way, depending on what the upper bound is. So I'm going to say my integral is from where to where of f prime of x. Where do we think? A to, well, it's going to be somewhere, and you have to say where that somewhere is, but it's still going to be a variable.
C.
You could say c. You could say whatever value you want. I'm going to use x in this case. That can be a to x1, a to x2, a to some x value, some x coordinate.
But can't you not have the same variable in the integral as...
Oh my gosh, you are totally correct. Let's go back and make this technically correct. I'm going to do f prime. You're totally correct, Ben. I'm sorry that I did not catch that sooner. It should be f prime of t dt. You can't have the same variable up here that goes in here. So I'm going to go from a to x now of f of t dt. Yeah, good catch.
How do you know when to not put?
The bounds, these guys can never be the same variable as inside. So Ben saw, oh, that's an x. Well, clearly inside here can't be an x. So I could have said c up here, as Ben said. Or if I want to make this x, I like putting this as an x because it's an x coordinate. So it makes more sense to put that as an x and change the inside.
So, okay, so you can't use the same letters as the one that's on the integral.
Yep.
But you can use any letters for f prime of something? Like say f prime of s?
Well, generally they'll define what it is a function with respect to. So I should have said it is a function with respect to t from the very beginning.
So it's either x or t.
I mean, generally speaking, yes, but I could say I have a function of money. I could just do a money symbol in there. It doesn't even need to be a letter, theoretically. But in the AP test, it's usually going to be f prime of t, f prime of x, something like that. All right, what I'm about to do is I'm about to prove, informally, the second fundamental theorem of calculus. So let's assume that I have a function, and this is it's so close to an actual AP question, it kills me. Like, this is how they define a function on the AP test. They'll be like, okay, a function is defined as the integral, an accumulation integral from a to some value of x, f of t dt. I'm going to take the derivative of both sides with respect to x. So let's go ahead and do that. I'm going to take the derivative d dx of the left and d dx of the right. I'm going to take the derivative with respect to x of both of these. And by the way, it should be mentioned that x, this is some x coordinate. So I'll say this is some x coordinate, and a is some number. It's a constant. So a is a constant. And if you don't like the word constant, you can put the octothorpe or the hashtag. It's some number. All right. So now I'm left on the left-hand side with g prime of x, and you will be taking the derivative of this accumulation integral. You will be doing this on the AP test. So try to get as comfortable as possible. Let's go ahead and assume, let's write this on the outside. Let's assume that if I take the antiderivative of f of x, that's going to be equal to capital F of x. And sometimes they define it, the inverse of this, they define it as the derivative of capital F of x is equal to lowercase f of x. This is more typical of a way to define what capital F of x is, but we know that the antiderivative of lowercase f is capital F. We've seen that before. We're comfortable. They do the same thing over and over on the AP test. So if you ever see capital F, you think, oh, they're going backwards from lowercase f. So far, so good. All right, so if I'm going backwards, I'm taking the antiderivative of capital F. I'm just going to leave this derivative here on the outside. I'm not applying this derivative, d dx. Let's go ahead and actually apply the integral. I'm going to deal with the derivative later. Let's apply the integral. Well, the integral of lowercase f, I just told us, is capital F, right? So it's going to be capital F of t, evaluation bar between a and x. So far, so good? We've seen this before. Okay, now I'm going to just go to the next line. So g prime of x, nothing has changed on the left side. I'm not going to apply the derivative yet. I'm going to leave that until the very end. And when I plug in so when I plug in my bounds, I'm going to start my square brackets here just to let you know I'm about to do a bunch of stuff. I have f of x minus what? F of a. Now I'm going to apply the derivative. I'm going to apply the derivative. This is kind of like the distributing the derivative. I'm taking the derivative of capital F of x, taking the derivative of capital F of a. And again, a is just some constant. I said that from the very beginning. So f of a is some number. This whole thing right here is just some constant. This again is just a constant right here. All right, so help me. What is g prime of x? G prime of x is I have to take the derivative of capital F of x. I've defined it over here what that is.
Oh, so it'd be f of lowercase f of x minus f of a.
F of x. I should have turned that off. And then you have to be careful. Let me just turn this off so it doesn't waste battery. So you are correct, Ben, that the derivative of capital F of x is lowercase f of x. That's defined on the left-hand side over here. But what is the derivative of a constant? What's the derivative of 5?
0.
0, yeah. So f of x plus 0. There it is. At g prime of x is just equal to f of x.
What's f of x minus 0?
I guess if you want to say f of x minus 0, you can say that. But the main thing here, and I'm going to write it in red because we'll be rewriting this anyway on the next page, but g prime of x is equal to f of x. Look at the first line, look at the second line. If g of x is defined as this integral from x, or from a to x, where a is a constant and x is a variable, some x coordinate. Maybe I should put variable also. Variable. Notice that when I take the derivative, I literally just plug in x. Go ahead and draw this in your notes also. This x basically gets plugged in here, f of x, and that is the answer. When I take the antiderivative and take the derivative of that, I'm literally plugging in that variable. And that's all there is to it. They are going to be giving you an accumulation integral and asking you to take the derivative. Literally just plug in that x value. There's no derivative here because I've done the inverse of it. All right, I don't know if I'm beating a dead horse or whatever. Let's come down here to the second fundamental theorem of calculus. Here it is. If you assume that a is a constant, so again, we're going to assume that a is a constant, and we're going to assume x is a variable. I'm going to just do VAR, abbreviate. If you assume a is a constant and x is a variable, what is this thing equal to? F of x what?
F of x.
Yeah, just f of x. Just f of
What
x.
about negative, because the order's reversed.
Well, I'm going to assume that this, whatever value that we plug in here is going to be greater than a.
Oh.
So again, if you want to, again, this is where we have to battle between, should I make it simple and make sure that everyone understands, or should I be very precise and then lose a few people? If you want to be very precise, you can say, assume x is greater than a. Otherwise, you will have to switch those bounds. Cool. And the chain rule on the second fundamental theorem of calculus, you won't see this probably ever on the AB version of the test, but I just wanted to just mention it here for those of you that are curious, like, why the heck is this really happening? So now I'm going to assume for this second case where I'm doing the chain rule that both v and u are both variables. What happens if I have two variables? You won't see this on the AP test. I'll make a note. This guy, not on AB test. This is just to satisfy my curiosity and your curiosity. Because I didn't actually know this before I was researching for today's notes. If u and v are both a variable, then again, you just plug in v, so I get f of v. And then I multiply this, after I plug in that v, I multiply by the derivative of whatever this thing is. So the derivative of x is 1. We're really multiplying this by 1. You just didn't know that. I'm kind of hiding that in the background. Now I'm formally telling you, you plug in v and then multiply by the derivative of v with respect to whatever I'm doing it with, so with respect to x. That's the first half. And then the reason why we don't have any second half, we don't have anything on the bottom, is because I subtract. Again, you plug in u. So it's going to be f of u, and guess what you're going to multiply by? Guess what you're going to multiply by?
dv or du over dx.
There it is. du over dx. Notice what happened here in our second fundamental theorem of calculus for this accumulation integral. This is a constant, so the derivative of a constant is always 0. This value here usually goes to 0, which means we don't have any of this second term at all. That's the reason why this is so easy, so nice. So again, you don't need chain rule. That's not going to be on the AB test. I just want to explain what happened here. And if that was confusing, ignore it. Just know that when I take the derivative of an accumulation integral, you get f of x, or f of whatever variable is up there. So far, so good. That's all I have for you guys.